All right, welcome back to Mathematics 0110. Here is part 2 of the video set on graphing functions using calculus. In the last example, we graphed a polynomial. In this example, it's not a polynomial, it's a nasty looking function. And you might not be able to guess what it looks like by looking at it. Does it have any max? Does it have any min? Maybe it has neither. What's its overall shape? This is not a typical function that we see that we were asked to make a sketch of. That means we have to trust the process. We have to trust calculus to tell us what the sketch is. This problem, like the last one, helps us through the process of making the graph by explaining what the steps are. It also contains some hints. One hint is the first derivative is given by that thing that's f prime of x. And the second hint is that the second derivative is given by that other thing. This is helpful in some ways, that we don't have to calculate these derivatives, but also means that there's no part marks attached to computing the derivatives. So the question is really emphasizing, it's really focusing on the new material. It's focusing on the material inside chapter 3 and saying, this is not a test of the quotient rule. We're going to assume you're good on the quotient rule. We're going to give you the result the quotient rule would tell you, and now see what you can do with it. See if you can draw the correct conclusion from it. Part A, find the intervals where the function is increasing or the function is decreasing. Increasing and decreasing are properties of the first derivative. So we'll do the usual thing. We'll set the first derivative equal to 0. So negative 54x over x squared plus 27 squared equals 0. We also need to check, where does the first derivative not exist? So the second piece here, the second place where critical numbers can come from, that would mean negative 54x over x squared plus 27 all squared does not exist. And that's never going to happen. This function always exists because in the denominator, look what we have. We have x squared plus 27. X squared has to be positive. You're adding a positive number to that. There's no way you can get a 0 in the denominator. So this function exists for all x. This derivative exists for all x. Cannot divide by 0. That's the only way that a rational function can have a place where it doesn't exist, is have a division by 0. Now the first one, we will find a critical point. We can solve by cross multiplication. Negative 54x is equal to 0 multiplied by x squared plus 27 all squared. Negative 54x is equal to 0. We get one solution, x is equal to 0. That tells us where to cut our number line. Let's think about the domain. We can't possibly have division by 0 in the original function because we have x squared, which is positive, plus 27, which is positive. We can't have 0 in the denominator. And there's no number that we're forbidden from plugging in. That means our domain goes from minus infinity to infinity. We can cut this number line at 0, at the critical number that we found. Now we need to choose two test values. One test value to the left of 0, one test value to the right of 0. I'm going to choose -1 and +1. And what we do with these test values is we plug them into the first derivative. So f prime of -1, so that's negative 54 times -1 divided by 1 plus 27 all squared. -1 squared is +1. We have negative times negative, so positive upstairs, positive downstairs. So positive over positive is positive, and that means it is increasing on the interval from negative infinity to 0. I'll draw a little up arrow for that. Use a different color for the second test value. Now we're going to plug that into the first derivative. F prime of 1 will have negative 54 times 1 over 1 plus 27 all squared. We have a negative on top, a positive on the bottom. That's an overall negative. And that means that the function f of x is decreasing on the interval from 0 to infinity. So I'll draw that with a down arrow. That's it for part A. Part B. Based on what we just saw, we can determine the coordinate, the x-coordinate at least, of any local max or min of f of x. Looking at the diagram, we have a max. It's going up and then back down, which indicates a local maximum. So local maximum, local max at x equals 0. The y value will be f of 0, which is negative 0 squared over 0 squared plus 27, which is 0 over 27, which is 0. 0 divided to 27 equal pieces. So local max, just to summarize, at 0, 0. And we'll have to store that for later when we make our sketch. Right, part C, find the intervals where the function is concave up and concave down. This is where we need to rely on the second derivative. So concavity from f double prime. So here we set the second derivative equal to 0. So 0 is equal to, well, I'll draw it this way. I'll say f double prime of x equal to 0. It doesn't matter which is on the left and the right, but I'll be consistent with the last page. So we have 162 times x minus 3 times x plus 3, all divided by the stuff that's downstairs, x squared plus 27 all cubed equals 0. And we also have f double prime does not exist. Solve f double prime of x does not exist. So 162 x minus 3 times x plus 3 over x squared plus 27 cubed. This exists everywhere for the same reason the first derivative exists everywhere. We can't get 0 on the bottom. It's not possible to get 0 on the bottom, so there's no solution, there's no x-coordinate where it could switch concavity that comes from that part. You have to go to the first part, though, setting the second derivative to 0. We cross multiply. 162 times x minus 3 times x plus 3 is equal to 0, multiplied by x squared plus 27 cubed. 0 multiplied by anything is 0. So 162 x minus 3 x plus 3 is equal to 0. We get two solutions. We get x is equal to 3, and we get x is equal to negative 3. Next step is we make our number line. By the way, these are not critical numbers. Critical numbers only come from the first derivative being 0, or the first derivative not existing, as long as you're in the domain of the function. These could be points of inflection, but not critical numbers, not max or min. Okay, so we're going to cut this number line at these x-coordinates, putting them in the correct order, so putting them from most negative to most positive, so negative 3 first and then positive 3. Next step, Recognizing that we have 3 different regions, we're going to need 3 different test values. I'm going to pick -4 for the first. I'm going to pick 1 for the second. And I'll pick 4 for the third. And I'll change the color in the middle. Yes, you can pick 0 if you want, but I don't want to pick 0 because it looks like a special number, and it's not a special number, it's arbitrary. Okay, and what do we do with these? We're testing to see if the second derivative is positive or negative in each of these 3 regions. So f double prime at -4. We have 162 times -7 times -1, all divided by something positive. Since what's in the denominator can't be negative, doesn't matter what you plug in for x, we get a positive output. That means the function is concave up inside this region. Long interval from -infinity to -3. All right, now we do the next test region. Second derivative evaluated at 1. So I'll have 162 times, where are we? 1 minus 3, so -2, and 1 plus 3, +4, divided by something positive, which is negative overall. That means concave down. On the interval from -3 to +3. All right, and we have one more test value. It's going to be concave up, up to a power of 4. I guess I shouldn't write that in. F to the power of 4 is 162 times 4 minus 3, 1, 4 plus 3, 7, over something positive. We get something positive. That means concave up. Now we'll draw it in from 3 to infinity. Okay, so those are our 3 different regions of concavity. Part C is finished. Part D, determine the xy coordinates of any points of inflection. From the diagram in part C, we see that f of x has POI at x equals 3. We need the y value. Y is equal to f of 3. So that's going to be -9 over 9 plus 27. So -9 over 36, which is -1 over 4. We're going to have to make a sketch of this, so knowing that 1 over 4 is 0.25 might be helpful. -0.25. And we have a second point, x equals -3. Y is f of -3. So that's going to be -9 over 9 plus 27. It's the same. So it's also -1 over 4, which is -0.25. So I'll summarize these two. POI at 3, -0.25 and -3, -0.25. And it's perfectly fine that they're the same y value at both points of inflection. That can happen, and in this case it indeed does. Okay, part E, determine the vertical and horizontal asymptotes. Well, one of these is really simple. That's the vertical. The vertical is a simple one to look for because the bottom of the original function is never 0. So I'll put that down. no vertical asymptote for this particular rational function, since denominator does not equal 0 for any x. That's the only way you can get vertical asymptotes for rational functions. Keeping in mind that just because the bottom is 0 doesn't guarantee it's a vertical asymptote. The top has to not be 0 at that point to have that guarantee. So if you've got 5 over 0 on a particular x coordinate, then that's a guarantee that you have a vertical asymptote there. But 0 over 0 could be a hole or could be a vertical asymptote. You have to take a limit and confirm that you have the value of the function going to plus or minus infinity at that point, the definition of vertical asymptote. Horizontal is more interesting. Horizontal asymptote comes from a limit as x approaches infinity. So limit x approaches positive infinity. It works out that for this function, the minus infinity limit is the same. When x approaches infinity of negative x squared over x squared plus 9. This is an infinity over infinity indeterminate form. So what I'm going to do is I'm going to divide the top and bottom by x raised to the highest power that appears in the expression. So x to the power of 2. Yes, you can use a shortcut if you want, but I don't feel like using a shortcut. Do it the long way. Negative x squared divided by x squared over x squared plus 9. So I'll divide x squared over x squared. So everything on top gets divided by x squared. So I get negative 1. Everything on the bottom gets divided by x squared. So I get 1 plus 9 over x squared. Then I take the limit as x approaches infinity and use the special theorem from the previous video lesson series, last week I guess. So minus 1 over 1 plus 0. So I get negative 1. Thus, horizontal asymptote of y equals minus 1. What this is saying is the function's y value flattens out to negative 1 when x becomes infinite, and if you take a limit to minus infinity, you'll find the same thing. Also, it flattens out to y value of minus 1 as x goes all the way to the left, which in the video I just pointed to the right because it's flipped. I do know my left from my right. Okay, now let's make the graph. Let's put the ingredients together and make the sketch. The dots have to go down. There's a max at 0, 0. So I'll plug that in. That's our max. Now, where are the points? And there's no min. And where are the points of inflection? We have a point of inflection at negative 3 and negative 1/4, and positive 3 and negative 1/4. So negative 3 and negative 1/4. So that's our POI. And positive 3. That's our POI there. Now, the vertical asymptote is absent. There is no vertical asymptote. The horizontal asymptote of minus 1. I'll put that in. So that's a horizontal asymptote. Okay, and I think I need to get these POI words out of the way. They might be in the way of the picture. Okay. Now we need to look at the increasing, decreasing information to see how to connect the dots. Our increasing, decreasing information is the function is increasing to 0 and then decreasing afterwards. So I'll put that in. We have increasing followed by decreasing. And that's forever. Forever on either side. Now the concavity information. It as concave up to the left of -3, and then concave down between the 3's and concave up again. So it's going up, down, and up. I have to use a different color for that. I'll use blue. So it's switching at 3. It's concave. Oh, I've already forgotten. Up. So it's concave up here, concave down there, concave up here. So let's do the first POI with the max. Connect those dots. Okay, so it's increasing and concave down, so it has this shape. Then between the max and the next POI, it's still concave down. Now it switches to decreasing, so concave down and decreasing is this shape. Concave down plus increasing. This one's concave down plus decreasing. Now we have the other regions. And these are tougher. Okay, to the left of the first POI, the function is increasing and it's concave up. So it has this type of a shape. Increasing, concave up looks like that. And it's approaching the y value of the horizontal asymptote. So I'm going to draw it like this. It's approaching this y value. Now it doesn't dip below it and then go back up because there's no other max or min. So it's doing that. So it is increasing plus concave up. So it's starting off on the bottom left and its y value is going up as it moves to the right. So increasing. Concave up, bowl facing up. To the right of the second POI, it's decreasing in concave up, so it has this shape, and it also has to approach the horizontal asymptote as x goes to infinity. So it's doing that. So decreasing plus concave up. That's it for that question. Okay, and we'll do this next problem in another video.